All right. So we're in chapter 2.4. We're going to be looking at chemical formulas. And just discussing how those formulas work, how we can calculate masses based off of that. We're going to define the amount of what a mole is, a quantity of a mole, and Avogadro's number. Okay. So let's look first here at what is a molecular formula. So when we have all these terms, molecular formula, structural formula, chemical formula, what does that mean? So first off, what is a molecule? We should define that. So there are two different types of compounds. There are ionic compounds and there are molecular compounds. Molecular compounds are what we call covalent compounds. So the difference between that is something that is ionic means that you have two things like sodium and chlorine, which are in ion form. So we have a cation of sodium, an anion of chlorine, and then they come together and they form an ionic compound, sodium chloride. Okay? So the ionic formula here is NaCl. We also have another name for that. We say it's the empirical formula because these salts or ionic compounds, they come together in only one way, just one single combination between them. And the formula that we see there is a representation of a crystal. And that crystal is designed of sodiums bound to chlorine, bound to chlorine, bound to sodium, bound to chlorine. And so it's forming a crystal, right? Sodium here, and then a chlorine here. Okay, so in this fashion, they're forming a crystal. And it's not asking how many sodiums and how many chlorines are in the crystal. It's just saying, what is the ratio of sodiums to chlorines within that crystal? And it's 1:1, right? For every one sodium, you have one chlorine. That would be different than something like magnesium and chlorine. Because now, for magnesium and chlorine, you have a 2 positive magnesium and a Cl negative. Well, how many chlorines do I need in order to give up 2 negative charge, two electrons, which is what magnesium did? 2. I need 2 chlorines to do that. So I need another chlorine. So the formula here is not MgCl, it's MgCl2. So magnesium chloride is going to come together different than sodium chloride, and it's going to form a crystal of 1 magnesium and 2 chlorines. So the ratio in the crystal for magnesium chloride would be different than the ratio of sodium and chlorines. So the ratio is 1:2 for magnesium chloride, whereas for sodium chloride it's 1:1. Okay? So these are ionic compounds. There's only one outcome between magnesium and chlorine. You can only have one single outcome. Okay? But when you have a molecule, you're not stealing electrons, transferring electrons like ionic compounds do. You're sharing electrons. So in other words, if I have one hydrogen here, and it has 1 electron, I'm going to show it with 1 electron. Okay? And then I have another hydrogen that has 1 electron. They each have a vacancy for an electron because overall they want 2 electrons. Hydrogen does. It wants 2 electrons. How do I know that? I know that because electrons like to pair together. They don't like to be apart. They want to pair. So when you have an electron that isn't paired, it wants to pair with something. So these guys, what they're going to do is they are going to share their electron. So now these electrons are going to orbit this hydrogen, and they're going to orbit this hydrogen. And we call that a covalent bond. So we have ionic bonds that come together by opposite charges like magnets, right? Like if you have two opposite poles of a magnet, what do? They stick together. Here we have covalent compounds where the electrons are not pulled onto each other separately, creating different poles, like magnetic poles. Instead, they are sharing the electrons equally. Okay? And by doing that, they're creating a bond, which is holding those two hydrogens together. This is a hydrogen molecule. Okay? So when you have a molecule, it is because it is a covalent compound. It's a shared thing. Like oxygen has 6 valence electrons. 2 of those are unpaired. So we get hydrogens that come in. Okay? And they have 1 single electron that they then want to share with oxygen. And then oxygen has 8 valence electrons, right? And each hydrogen has 2, which is what hydrogen wants. Hydrogen wants just 2 electrons, that's all it wants. Oxygen wants 8. And so by doing this, they have shared their electrons, and now these 2 electrons will orbit this hydrogen, and these 8 electrons will orbit this oxygen. And then those 2 around that hydrogen. And then these 2 electrons are going to orbit this hydrogen and this oxygen. And by doing that, they pull those hydrogens onto the oxygen and making a covalent bond. So we would say that this is a molecular compound because it is covalently bonded. So this is a water molecule. Okay? All right, so that's a water molecule. That's a hydrogen molecule. These are ionic compounds, which have empirical formulas. Empirical formulas are the ratio of the amount. They're not showing this. They don't have structures because they're just crystalline. Okay? They don't have structure like these. This water molecule has a structure to it. So molecules have structure to them. Ionic compounds are just crystalline. They don't have the same kind of format, that same structure format. Okay? All right. Now, within a molecular formula, you can also get, for bigger ones, for bigger compounds, these structural formulas. So when you look at a structural formula, you might think of something like carbon compounds. Carbon compounds are form molecular compounds, okay? And they like to bond to each other. So we might get carbons here, carbons, carbons. And if we draw the structural formula, we'd actually show all of the hydrogens within that carbon molecule structurally where they are, okay? So this would be the structural formula of butane. Like the gas that you have in your lighters, butane lighters, that's butane right there, okay? That's the structural formula of it. Or you could get line formulas. Line formulas would just be like this. That's the line formula of butane. What I'm not showing are the hydrogens in a line formula. All I'm representing are the positions of the carbons. Here's a carbon, here's a carbon, here's a carbon, here's a carbon. Those 4 carbons, like that. Okay? That's the line formula versus a structural formula. So that's the difference between them. Yes? don't include hydrogens on a line formula.
So how do you know that it's butane if you only get the carbons?
Because when you have a line formula, the only thing you don't show are hydrogens. So you know where you know how many hydrogens there are. Every carbon makes 4 bonds. If I can only see 1 bond on a carbon in a line formula, that means the other 3 bonds are hydrogens. Here, I only see 2 bonds on this second carbon. That means the other 2 bonds that I don't see are hydrogens. Okay? So everything you don't see is a hydrogen. Anything that you put there is anything but a hydrogen. And then the connection points are carbons. So it's just a simple, easy way to draw carbons and hydrogens really quickly.
So line formulas only work for carbon and hydrogen?
Well, if there's an oxygen on one of these, let's say that I had an oxygen here, then I would draw it. Or if I had a chlorine here, I would draw it. So I can build the structure out. But for organic compounds, which is mostly where you'll see these line structures, big carbon molecules, this is an easy way to draw them. Okay? Versus the structural formula, which might take a long time to draw if it's a very, very large molecule. Okay? Okay, here we see some other ways to see that. Here is a methane molecular formula of methane, Ch2.4. Okay, also known as the chemical formula in this case. Molecular formulas and chemical formulas can be similar. You can have some that have the same chemical formula or molecular formula, but different structural formulas. For example, C4H10. Four carbons. And we saw that one of those structures right here, butane. But I could have also drawn it like this. Okay? And here, once again, I have the structural formula of this methylpropane. A methylpropane. This is the methyl group, and this is CH3, which is a propyl group, or propane. So methylpropane. Okay? But both of them have this same chemical formula, C4H10. We say when you have the same chemical formula, different structures, that means that you're 2 different isotopes. These are isomers. I said isotopes. I meant isomers. Isotopes are the neutrons are different within an atom, right? So these are isomers. Iso, once again, meaning the same but different. Just like isotopes are the same element, but they're different masses. Isomers are the same compound formula but different structures. Okay, they're different. So that's what we would call an isomer. So you have this molecular formula here for methane. Here is the structural formula. You can also see it in a ball stick model. These are just models. And here's a field model of that. Okay? So when you look at this, you see these lines, right? Those are representing bonds. Once again, that line isn't actually a line. It's just a model, a representation of what's happening. What are we saying there when we draw a line? That 2 electrons are being shared between both the carbon and the hydrogen. But if you looked at it under a microscope, a high-powered microscope, would you see a line? No, that's not what you're going to see. It's just a model to represent what we mean. We mean 2 electrons are shared between the carbon and the hydrogen. That's what we mean. Yes? You would see a little bit more like this. Like they're kind of coming into the same space. These these two atoms filling up into the same space, and they're kind of blending together into, like here's a methane, right? And a lot of that has to do with resolution. The resolution of a microscope, can you actually see what's between these two things, like the space there? And an electron microscope, what it does is it shoots electrons, right? And so that's a high powerful electron microscope. It's shooting electrons, trying to get those, a profile of what that molecule looks like. So there's different types of microscopes. Scanning tunneling microscope, kind of like at a pinpoint, shows different features. And so we don't have enough resolution to see exactly what it looks like, right? That's all we're saying. You can kind of get an idea of what it looks like. But on that scale, the atomic scale, we don't have enough resolution. Okay. So, a lot of elements can exist as discrete individual atoms. Mostly the noble gases. The noble gases will exist as a gas because they're non-reactive. They don't need each other to exist. But that's not the same as some of these diatomic molecules that we see here, because they need one another to fulfill electron vacancies, like we saw with hydrogen, right? Hydrogen has one valence electron. Does everybody know what I mean when I say valence electron? Okay, it means, that's right, the outer shell electrons. How many electrons? And that's where chemistry takes place, is on the outside. On the outside, not the core electrons. It doesn't take place by core electrons, the ones on the inside. It takes place on the outside electrons. So if I have a nucleus, and I have these electron clouds that are surrounding the nucleus, if I have electrons on the inside, they are not participating in the chemistry. So that's why I ask how many valence electrons there are, not how many electrons does this element have. How many valence electrons is a better question, because those are the electrons that are participating in the reactions. Okay? So if I have electrons out here on my valence shell, okay, like if I have 3 unpaired electrons on my valence shell like this, then that tells me something. That means I can make like 3 bonds, because I have 3 electron vacancies that I need to fill. So if I had 3 hydrogens, I could take those hydrogens and I could pull them into these vacancies, right? Let's put it here. And now I have 1 hydrogen there, and you could imagine I could have 2 more hydrogens at the other vacancies. And I would create these covalent bonds, right? And if that was ammonia or nitrogen, then it would become NH3, which is ammonia. All right? So this nitrogen molecule right here could bond to 3 hydrogens, and we could create ammonia. But hydrogen on its own, because it has 1 electron, is not stable. So it needs a second hydrogen with 1 electron to become stable. And so we get, instead of just a single hydrogen, hydrogen exists as an H2 molecule. Okay? Or oxygen. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Okay? Has 6 valence electrons. Let me see. That's fine. Let me draw it a little different. 1, 2, 3, 4, 5, 6. Okay? It has 6 valence electrons. 2 of those valence electrons are unpaired. Okay? 2 of them are unpaired, and the other ones are paired. So here are the paired valence electrons, and the other ones are single individual unpaired electrons. So, how do we help oxygen exist? Well, we get another oxygen that has 2 unpaired electrons and 2 paired electrons. And now we have just created what we would call a double bond. So hydrogen has a single bond, which is represented by a line or 2 electrons. So H is H2. Whereas oxygen would create a double bond where these would be the bonds, right? So you're going to get oxygen, and it has these unbonded electrons out here, which we call lone pairs. These are called lone pairs. Okay, so you have those lone pairs, and then you have the 2 bonds, which means you have a double bond. Look at nitrogen. Nitrogen, once again, it has 1, 2, 3 electrons that are unpaired, and then 1 pair of electrons that is paired. So if we get another nitrogen with 1, 2, 3 unpaired electrons, you will create a what? A triple bond. Now we have a triple bond. So nitrogen with its triple bond, that's how nitrogen exists, as diatomic N2, or diatomic O2, or diatomic H2. Fluorine has 7 valence electrons. 1 of its electrons is unpaired. So we get another fluorine with 1 unpaired electron. How many lone pairs does fluorine have? There's 1 of the fluorines. How many? 3. So this fluorine has 1, 2, 3 lone pairs. And it has a what kind of bond? A single bond. So each fluorine has 3 lone pairs and a single bond. So we have a single bond with 3 lone pairs. Okay? This is fluorine, or F2. Okay? Fluorine does not exist as a single fluorine. Oxygen does not exist as a single oxygen because they're not stable in that form. They need each other to become stable. Okay? That's why we have all of these diatomic molecules here. Diatomic H2, N2, O2, F2, Cl2, Br2, and I2. These guys are what we call the halogens. They each have 7 valence electrons. Look at your periodic table. Fluorine, chlorine, bromine, and iodine. Do you see how they're all grouped together in the same family on the periodic table? In group 17 there on the periodic table. Let's pull it up. Oh, let's see if my internet's working. Nope. Okay, we won't pull it up. Okay, so those are all grouped together on the same family, meaning they have the same valence electrons, and they each exist in the same way as these diatomic molecules. Okay? Oxygen, also diatomic. Nitrogen is diatomic. Carbon is not. Carbon is not diatomic. Okay? And then others exist as even more than diatomic, like sulfur here. S8. Okay? So we have, like, in this fashion. It's going to form this sulfur ring octahedral. Okay, an octahedral ring. Okay. So there you go. For if you're talking about the nomenclature, you would say this is 1 hydrogen atom. This is 2 hydrogen atoms because they're individual separated hydrogen atoms. This is 1 hydrogen molecule which means that there's 2 hydrogen atoms, but it's 1 molecule, right? Here is 2 hydrogen molecules. So, for example, if I was to say hydrogen plus oxygen reacts to form water, this is what you would not write. H plus O forms H2O. Okay? That is incorrect. Instead, what I would write is H2 plus O2 forms H2O. That is the correct way to write that. And then obviously we would want to balance it because it's not the correct amounts, because here I have how many oxygens? 2. And over here I just have 1. So I need to get 2 water molecules to have 2 oxygens. And I need, because I have 4 hydrogens now from 2 H2s, I need another 2 H2 here to give me 4 hydrogens. So I have 2 hydrogen molecules. 1 oxygen molecule will form 2 water molecules. Okay, so that would be the nomenclature I would use when I'm trying to describe this. So if hydrogen and oxygen reacts, I don't write this. That's incorrect, because that is not how hydrogen exists. Okay. We talked a little bit already about an empirical formula. Empirical formula meaning that it's the lowest ratio formula. Okay. Molecular formulas can also have empirical formulas. You would just need to put them into their lowest ratio. So for example, here we have C6H6, like benzene, the molecular formula for benzene. And if I was going to write that as an empirical formula, I would just divide it by 6 to put it in its lowest ratio of CH. Here's another interesting one, C2H4O2. If I reduce that to its lowest ratio, I would divide everything by 2, and I would get the empirical formula of CH2O. Now that's a interesting empirical formula because it relates to the idea of something like this. Does anybody know what that is? Sugar. Glucose. Or fructose or galactose. It's one of the monosaccharides. It's the molecular formula of a monosaccharide, glucose, galactose, or fructose. Okay? C6H12O6. We mostly know it as glucose because that's what we talk about in biology as the molecule that provides us with the energy of ATP, right? So that's why we think of that. Or from cellular respiration. C6H12O6 plus O2 forms carbon dioxide and water. Cellular respiration, or the backwards reaction, is called what? Photosynthesis, right? So cellular respiration or photosynthesis, right? So that's where this is coming from, this sugar C6H12O6. Now, what is the empirical formula of glucose? What is its empirical formula? CH2O. Now, what are some terms or names that we could use for sugars? Anybody know any? We can call them monosaccharides, but what else can we call them? Call them by their names, like glucose. Any other names that you guys know? I'm going to tell you one here in a second. Okay, so there we go. A carbohydrate. Carbohydrate. Because we have a carbon, water. Because the empirical formula of any sugar is CH2O. That's the empirical formula of it. And so we call those carbohydrates. And that's why. Okay? I know you guys are blown away by that. But that's why we call them carbohydrates. All right? Okay, so that's the long story short to get to this empirical formula. So this also could be a sugar molecule. Okay? Is the simplest sugar. But anyways, they will have that molecular formula of Ch2.4. Oh, this one's acetic acid, so that is not a carbohydrate. Okay, here once again, we see a compound, and this titanium dioxide, or this titanium 4 oxide, is forming a crystalline structure, and it's the ratio of the oxygens to the titaniums that are forming that structure that we care about. 1 titanium for every 2 oxygens within the structure. That's how that structure would form. Okay. Oh, darn it. This is not good. So let's look at defining the amount of a mole related to quantities and Avogadro's number. So let's talk about that for a second. Okay. So what is a mole? A mole, if I said to you a dozen, you would tell me what? 12, right? And that could be 12 anything. 12 eggs, it could be 12 pencils, it could be 12 basketballs, it could be 12 of anything. So I've categorized it as a dozen. That means there's 12 of them. The mole is exactly the same. 1 mole is equal to 6.022 times 10 to the 23rd. Okay? So 6.022 times 10 to the 23rd, and that could be of anything. If you have a mole of basketballs, it would be 6.022 times 10 to the 23rd basketballs. If it was a mole of pencils, it would be 6.022 times 10 to the 23rd pencils. If it's 1 mole of eggs, it's 6.022 times 10 to the 23rd eggs. But we don't use it for that. We use it for atoms, for molecules. Okay? So if it's a mole of an atom, that means you have 6.022 times 10 to the 23rd of that atom. If you have a mole of molecules, you have 6.022 times 10 to the 23rd of that molecule. So 1 mole of water would be a mole of molecules, water molecules. A mole of carbon would be a mole of carbon atoms. Okay? So that's how we look at it or define it. There is one other unit that we use with that number, and that is formula units. The formula units are for ionic compounds. That means the empirical formula of an ionic compound is the formula unit. Okay? So you could have 6.022 times 10 to the 23rd atoms, or 6.022 times 10 to the 23rd molecules, or 6.022 times 10 to the 23rd formula units, depending on what you're working with. Okay? For example, if I have 8.65 times 10 to the 24th atoms, and let's say it's carbon atoms, and you want to know how many moles of carbon do you have if you have 8.65 times 10 to the 24th atoms of carbon. Well, then we want to convert that from atoms to moles from the atoms. Okay? And so I need this conversion factor. There are 1 mole for every 6.022 times 10 to the 23rd atoms. Okay? And so then you can see here the atoms will cancel. I'd be left with my moles. And that's how this would work. So, why do I say that every time? So let's grab a calculator. And it's best if your calculator can do significant figures, okay? Meaning that it has a, so I'm going to change mine to a scientific calculator so I can do the EXP button right here. You would want a 10 to the X button, an EE button, so a button that is either EE or EXP or 10 to the X, something like that. That's the button you're looking for to use the scientific notation, because the scientific notation is going to be important here, okay? So I want to take 8.65, and if you have a calculator, I'd recommend trying this, because the way that you enter this into your calculator will tell you if you have a calculator that can enter it without parentheses, or if you have to use parentheses, or those sorts of things, okay, when you're doing the scientific notation. So let's go ahead and do this. So we're going to say 8.65, and we're going to use the exponent times 10 to the 24th, okay, and we're going to divide that by 6.022 times 10 to the 23rd, okay, and I'm going to get 14.4. 14.4 moles. So this is equal to 14.4 moles. Okay. How are you guys doing? Is that what you're getting? All right, so we get 14.4 moles when we do that. Now, another way you can know if you're getting the correct answer or not, even if you haven't done the entered it into your calculator correctly or whatever, is you can always take 8.65 and divide it by 6.022. Okay, so what happened to my calculator? So 8.65 divided by 6.022, and that is 1.43. Okay, or 1.44. All right, it's 1.44. Now I can take 24 and minus 23 because this is division. 24 minus 23 is 1. Okay, and so that means I need to take 1.44 times 10 to the 1, which means 14.4. So it's the same. Okay, so you can always do the division that way too. If you're doing division, you subtract exponents. If you're doing multiplication, you add exponents. So you can always add the exponents to get an idea of where you should be, or you can always subtract the exponents to get an idea of where you should be. Okay? So that's just a simple way to make sure you're answering the question correctly. All right? Okay. Okay. So this is the mole. So the other thing is that on our periodic table, okay, there are masses. We've talked about those masses, right? The atomic masses. Like carbon has an atomic mass of 12.011, let's say. Carbon equals 12.011 atomic mass units. That is the average atomic mass of carbon, including the carbon 12s, the carbon 13s, and the carbon 14s, right? Now, it is also, carbon is equal to 12.011 grams of carbon for every mole of carbon. So, if I get a sample of carbon and I get exactly 6.022 times 10 to the 23rd atoms of carbon, which includes the carbon 12, 13, and 14, right? I get a sample of it, and I weigh it out to 12.011 grams, it will equal, that means I have 12.011 grams of carbon is equal to 6.022 times 10 to the 23rd atoms of carbon. So, the amounts you find on the periodic table, they are conversion factors. They are conversion factors. What if I have, let's go this way. What if I have 186 grams of carbon? How many moles of carbon do I have? Well, let's convert it to the moles of carbon from the grams of carbon. Well, here I have this conversion set up. What number am I going to put on top here of this conversion factor? 1 mole of carbon for every, well, this is grams. If it was atoms, molecules, or formula units, I would use 6.022 times 10 to the 23rd. But that's not what I'm doing here. I'm not converting from those. I'm converting from grams. Where do I find that gram number? On the periodic table. 12.011 grams of carbon for every 1 mole of carbon. Okay? That's what I'm going to use. And then I can say 186 divided by 12.011, and that's going to give me the moles of carbon that I have in 186 grams of carbon. What if I want to take 186 grams of carbon and find out how many atoms I have? How many carbon atoms are in 186 grams of carbon? Well, I got to get rid of the grams of carbon to go to the atoms of carbon. Now I'm going to still use the 12.011. Anytime I have the unit gram, where do I find that unit? Periodic table. Anytime I have the unit mole in a conversion factor, I'm going to put the number 1. Now that's for these kinds of conversions, but when we get to stoichiometry, that's going to be different. But for right now, gram to mole conversions, moles are always 1. Grams I find on the periodic table. If it's atoms, molecules, I'm going to use what number? 6.022 times 10 to the 23rd. So what number am I going to put on top of this conversion factor right here? 6.022 times 10 to the 23rd atoms for every 12.011 grams of carbon. Okay? That's the equivalency between them. So that's how I would set it up. I'd say 186 times 6.022 times 10 to the 23rd divided by 12.011. And that would be how I find out how many atoms of carbon are present. Okay? So these are simple types of conversions that we can do in order to know how many, the amount of grams, the amount of atoms, or the amount of moles that we have in a substance. So our periodic table is going to be vital to us when we do something like that. So for example, if I have 76 moles of carbon dioxide, and I want to know how many grams of carbon dioxide that is from the moles of carbon dioxide, what number am I going to put on the bottom of this conversion for moles of carbon dioxide? Grams to moles, moles are always 1. I'm going to put 1 mole of carbon dioxide for every, and now we have carbon, which is equal to, let's just simplify it to 12, and then oxygen, which is equal to 16, but it's O2, so that's 32. So we have 44 grams of carbon dioxide for every 1 mole of it. Okay? So to see where I got those numbers, these numbers still came from where? periodic table. When I find the mass of the formula, that's how I do it. I have to find its mass by adding together everything that's present in the formula itself. Okay?
I'm sorry, I didn't get
Yeah, you bet. For the carbon dioxide mass?
Yes.
This?
Yes.
Okay?
Oh, I see it.
Let's see. Carbon, O2. Carbon, if I go to the periodic table, has a mass of 12. I'm simplifying that. You could use the whole thing, 12.011. Oxygen has a mass of approximately 16. 16 times 2 is 32. And so I add those together and I get 44 grams per mole. So that's the gram number that I'm going to use right there. And then it's for every 1 mole. Okay? So that's how I would do that. Now, sometimes formulas are a little more complicated than CO2, but the concept would be the same. So, for example, magnesium, let's put 3PO4, magnesium phosphate. Okay, if I want to find the formula mass for magnesium phosphate, I need to make a chart here. Magnesium, I'd find its mass. Phosphorus, I'd find its mass. Oxygen times 4, and I'd find its mass. Okay? So that's how I would go about doing this. So for magnesium, we have a mass of 24.3. For phosphorus, a mass of approximately 31. And then oxygen is going to be 16 times 4 is, let's see, 64 for that. And then we just add that all together. 3, 9. So we get 119.3 grams per mole. Okay, oops. I made the mistake I shouldn't have. I'm sorry. This is phosphorus, but there's 2 of them. That's what I meant to show you guys, and I got it carried away. And then how many oxygens do I have?
8.
Oh, 8, right? So that's actually, so what I did the first time is the mistake you shouldn't make. That's not what you should do. So when we find this mass, we need to include the factoring in. You're right. Absolutely. Okay. So I was in a whole different world there for some reason. Okay. So we would want to find all of those masses multiplied by the number that we have in the formula. So magnesium, Mg3, P2, O8, and then that's what I would use to find the masses of these, right? So with magnesium, 24.3 times 3, we're going to get 72.9. With phosphorus, we have, 31. 31 times 2, we're going to get 62. And for O8, we're going to take 16 times 8 and get 128. Plus 62 plus 72.9, and we're going to get 262.9. And that's how we'll find those formula masses. Okay? All right. Are there